Now, let's, I'm going to make an observation here, which is concerning this guy. What we want to understand is the effect of this kernel, and what does this kernel look like? This is the kernel of our transform. This is what's taking our information and encoding it now in frequency content. So I'm going to write down this function, the following, W n k, which is equal to e to the 2I pi k minus 1 n minus 1 all over n. Okay? And remember, here's the observation to make. Cosine, right? This is going to be equal to cosine of 2 pi k minus 1 n minus 1 over n plus I sine 2 pi k minus 1 n minus 1 over n. Cosines and sines. So this will be important because the Fourier transform uses a complex kernel, an e to the I, which is some collection of sines and cosines. And this is why when you put in a negative number in the coefficients here, remember when we do our Fourier transform, we go from negative Fourier components, like if we think about if we have 64, we pick n equals 64, we go from e to the negative I 32 all the way to e to the I 32. If this is positive or negative, it makes a difference right here. It's cosine plus I or cosine minus I. Okay? Now, we don't have to just use Fourier components just as they are. We can also think about using, well, what if I just use this? Or what if I just use this? Now, if you just use that, that'd be called a cosine transform. It's still based on Fourier modes, but you've taken out all your odd components. Or you could use that, which is called a Hamilton transform. No, it's sine transform. I'm just making stuff up. You would have bought it right if I said Hamilton, because he must be, sounds famous, like 1700s or something. Totally buy that. Sine transform, cosine transform. That's it. Okay? All right. So this is what we have. And notice that ultimately when we make the transform then to frequency space, here is what we are doing. We are constructing ultimately a vector multiplication problem where what we want to do is construct a vector of all frequency content given my space content, and I multiply by this vector here, omega nk, which is the frequency components, and that's what that piece is there. Mm-hmm.
Negative nk. There's a negative in the exponent of Fourier definition.
Well, so we use this as the kernel, and I could have made a mistake, sign mistake here. Perhaps this is a minus. Okay, let's leave it right now for like this, but probably I made a mistake. If you reverse the signs here, it still works right, because the Fourier transform, the one thing is, one definition is like this. Here's another one. They both work. And it could be that what I did is one here and then another here. All right? That just keep you loose and limber during class. Okay. All right. Some people do yoga before class. Some don't. They're all angry when they come to class. But Haley, she's relaxed, chill. Maybe you guys should all do yoga before class. Okay? MATLAB and yoga. Do they mix? No, I don't think they do. Okay, all right. Maybe it's a bad idea. Okay. Now, let's do a little observation here. I want to compute this Fourier transform. I have n components, and for each n, I have to do this matrix multiplication. I have to sum across a row. Do you know how much work it's going to cost me to do this? Order n squared. By the way, this is no faster than any other matrix multiply problem that we have. So at this point, you could say, well, Fourier transform is no faster than anything else. Because I still have to do this operation here. That costs me order n squared. And then you say, wasn't that guy talking about order n log n? And well, okay, we're going to talk about how do we get around this problem of going from order n squared to order n log n. So, but before we get down there, one of the things I want to display to you is here's a kernel, here's another potential kernel, here's another potential kernel. We could do Fourier transform, cosine transform, or sine transform. And what I'll show you is what basically you're going to do if you do these transforms and what the implications are. So let's start off first with the Fourier transform. So there, our kernel of the transform, right, is this e to the I 2 pi k minus 1 blah, blah, blah. Okay? Or if I want to write it a little bit more simply, it looks something like this. That's kind of your kernel of the transform. Okay? Now, what kind of functions, then, am I going to be representing here, then? Well, take, for instance, something like the first mode, which would be something like a j equals 0 or k equals 0. Well, then this becomes a cosine 0 plus I sine 0. What's sine 0? 0. Cosine 0 is 1. So your first mode is something like this. If you want to think about it in electrical engineering terms, that's DC component right there. Okay? Something that doesn't oscillate, cosine 0, that's your DC. I know, you guys are looking for the AC in the DC. We got a rocket this morning, which also doesn't go with yoga. I have no, you never see a yoga video to AC/DC, right? Or do you? Somebody was looking like, I wonder if okay, so if you find yoga to AC/DC, let me know. There's a class in Vancouver.
Heavy metal yoga.
Heavy metal. Nice. Shook me all night long to yoga. That's awesome. Let's go to Canada. We're going to do a field trip for this class. Hey, if you can do heavy metal yoga, you can certainly do MATLAB. All right. So there's mode 1. Now let's put in j equals 1 and have something like sines and cosines. And in fact, when you start calculating the modal structures, here's your next mode. And then your next mode. So this is 1, 2, 3. Okay, blah, blah, blah. Now, here's the thing to notice. So first thing you notice about this, right, when you do these is that, okay, so what kind of boundary conditions right away do we start thinking about? When we start, we're going to project all our information onto these modes. And notice, they have periodic boundary conditions. So what's on the left is on the right. What's on the left is on the right. Okay? So right away, when you have this, periodic boundary conditions. Now, I've already made a comment about that. It's periodic boundary. Okay? But now, if we use other kernels for the transform, in particular, for instance, if we do sine transform, for those of you from Europe, you might call it the sinus transform. Because I had a European roommate in grad school, and he and all his friends would say, do you take sinus of the angle? And this is great to have Europeans. And here it is. The sine transform is just now you're just doing things like this. That's your sort of kernel you're going to work with. And when you work with that kernel now you're going to work on a 2 pi periodic domain. And now your functions are going to look a little different. If you're using a sine transform, you never get a DC component. One thing to know. And what you're going to work with now are functions that go like this. You're going to do so it's like a sine of half the angle here. And then that's your first mode, second mode, third mode. You just keep adding, one at a time. 1, 2, 3. Sine functions.
Sine, is that a pi or a 2 pi?
Pi.
That's pi.
Yeah. And so here are your mode structures. Now, Now we ask the following question, what are the boundary conditions now? If I'm using this half angle thing, then notice where everybody goes from and where everybody ends up. 0 and 0. So if you use a sign transform, what you have is pinned boundaries. So u at 0 is equal to 0, and u at 2 pi equals to 0. So you start thinking about, oh, look, you know, if I have a boundary value problem, or if I'm doing a computation, which requires that at the boundaries the solution is 0, doing a sign transform is a pretty smart idea, because the sign itself preserves that boundary condition. Okay? Cosine, again, cosinus, and there you have the cosine of pi j k n as your kernel. And actually here we put a 2 on the bottom. We're going to do half angles. And then the first mode is a DC component. Second mode, cosine half, it's like that. Third mode, like that. What are the boundary conditions now? Certainly, you go from 1 to minus 1 on this side, or it could be 1 minus 1 on this side if you flip it. But at the boundaries, what are the derivatives? So if you take the derivative of cosine and get a sine, at the boundaries, the derivative is 0. That's what a cosine will give you. It will give you what's called no flux boundaries. So the derivative is 0, and sorry, I'm writing way down on this board, but I had to put all three stacked up or else it wouldn't look nice. Okay? So you go. So periodic, pinned, no flux. So there's a reason you choose different versions of this cosine transform. So when you do Fourier transform, the way you call it is just you say FFT U, right? You've already done that. We've already done it in class, right? So here's the command for this, FFT U. Sine transform, it's a discrete sine transform. DST U. Cosine transform, DCT U.